The James Webb Telescope has completely changed how we view the universe by giving unprecedented details of galaxies far, far away, and more details into the past, current, and future state of the universe. NASA continues to release more images from the telescope, and they are like nothing we've ever seen before. But how does Webb do what Hubble and other telescopes before it couldn't? Well, in today's video, we'll be taking a quick look into how the James Webb Telescope changed astronomy forever. Launched in December of 2021, the James Webb Telescope has since been providing astronomers with a dynamic look into regions of our galaxy that we've already mapped, but with so much more intriguing detail. In comparison, Webb is about 6 times larger than Hubble, with over 18 primary mirrors measuring 6.5 meters in diameter, as opposed to Hubble's 2.4 meter diameter mirrors. With this, Webb can observe and capture longer wavelengths of light with much more accuracy. Webb can do this with the use of 4 state-of-the-art instruments that enable it to operate at much lower frequencies than other telescopes, such as the Hubble Space Telescope. Webb's amazing instruments. Webb's ability to produce clearer and more detailed images of space is a combined result of its 4 primary instruments. These include the Near-Infrared Camera, or NIR cam, which allows Webb to see from the visible to near-infrared wavelengths of light. There's the Near-Infrared Spectrograph, or NIR spec, which enables Webb to observe hundreds of individual objects simultaneously from a single field of view. Then there's the Fine Guidance Sensor, and Near-Infrared Imager, and Slitless Spectrograph, or FGS NIR-ISS, which are used to stabilize Webb's line of sight during observations for image stabilization. Finally, there's the Mid-Infrared Instrument, or MIRI, which plays a significant role in Webb's stellar imaging abilities. MIRI consists of a camera and spectrograph that sees light in mid-infrared at wavelengths that are much longer than our eyes can see. This is because the further away light gets from its source, the more stretched and longer its wavelength becomes, until it's ultimately invisible to the naked eye. But MIRI is designed to be able to capture light through its primary camera, and using a complex series of filters and mirrors, split the light into different wavelengths. These wavelengths are then resized and redirected into the sensors, which allows for a much deeper field of view and improved imagery of redshift light from distant galaxies, faintly visible comets, and newly found stars. But Webb is only able to carry out these observations at temperatures near absolute zero. Why does Webb need to be so cold? Being an extremely sensitive astronomical telescope, the optics and scientific equipment present on Webb need to be incredibly cold in order to suppress what is known as infrared background noise. This noise, which causes poor image quality, is caused by heat sources that emit infrared radiation in the form of light. So the colder the telescope, the less heat and background noise is captured on camera. Scientifically, the longer the wavelength of light being observed, the cooler the telescope needs to be to convert these wavelengths into clear images without interference from infrared background noise. While 3 of Webb's 4 instruments can be cooled passively by virtue of the telescope's sun shield, MIRI needs to be at temperatures below minus 267 degrees Celsius, and as such the James Webb is fitted with a cryo-cooler dedicated to keeping MIRI at these temperatures. For comparison, Hubble is kept at temperatures of 21 degrees Celsius, and as such has higher incidences of background noise. Webb's pinpoint accuracy. Webb is indeed a state-of-the-art technology, but its technological intrigue isn't just in its ability to provide much clearer images of distant galaxies and stars, but also in the speed at which it carries out its observations. For comparison, the Hubble telescope takes about 3 weeks of observation to gather a single data image of a single spot in the sky, which, up until Webb, was an impressive feat. But James Webb can carry out the same observations in just 13 hours, and with much better data results and clearer imagery, making Hubble's 3-week observation look almost archaic. But this reduced observation window isn't simply because Webb is a much bigger and more advanced telescope, but also because of the difference in positioning between both telescopes. The Hubble telescope observes space while stationed in low Earth orbit, completing a trip around the Earth every 128 minutes, and as such, it has short windows of observation for each point in the sky. Webb, on the other hand, orbits much farther out, at the L2 Lagrange point, which is about 1.5 million kilometers from Earth, and orbits Earth roughly twice a year. This causes a significant difference as Hubble is occasionally obscured by Mercury, Venus, and Mars, while Webb has very little obstructions to its view. and can make observations with much clearer lines of sight and improved sensitivity. In essence, Webb is positioned to be much more productive, in addition to its state-of-the-art equipment, enabling it to produce the most detailed real-life images of the universe we have ever seen. Another mind-blowing aspect of the James Webb Telescope is its ability to view the individual spectra of whatever galaxy or cluster of galaxies it observes. Webb can observe the individual spectra of more than 100 galaxies in a single field of view, and what's more intriguing is its ability to view even the chemical spectra of these galaxies, enabling scientists to determine the chemical composition of each galaxy. So the data Webb provides can enable astronomers not just to tell the distance of each of these faraway galaxies, but also to decipher the individual molecules present in each of them. With data from Webb, scientists can read traces of hydrogen, oxygen, and even elements such as neon, which enables them to understand the current stage of development of these galaxies. Webb has opened up a new region of space exploration, as astronomers are now able to tell which distant galaxies have collided, which are experiencing star formation, and which primordial elements are currently being formed. By far, Webb gives us the most accurate depiction based on real-time data of what the early universe looked like a few 100 million years after the Big Bang. Deep field images. Webb has taken some really amazing images since its launch, and, at first glance, these might not look like much to the average person, but they're actually a lot more complex than they look. Let's have a look at some of them. Deep field image of galaxy cluster. This deep field image is one of the very first we've seen, and Webb was able to observe it in more staggering detail. It's important to note that this image had already been captured by the Hubble telescope, but with not nearly as much accuracy as Webb did. In this image, we see a galaxy cluster that's taken about 5 billion years for its light to reach us, which is almost the same age as our solar system. For comparison, you can see the amount of detail that Webb provides as opposed to Hubble. The Southern Ring Nebula. This image is of a dying star, also known as a planetary nebula, located some 2,500 light-years away from Earth. The amazing thing about this nebula is that it's a widely observed star cluster and has also been captured by the Hubble telescope before. With both images, we can actually do a side-by-side comparison, and it's obvious the difference in the detail in both images. We can clearly see that Webb's version of the nebula is much more detailed and frankly just more beautiful to look at. This nebula is a dying star surrounded by rings of planetary gas and dust, which is probably what our sun will look like billions of years in the future as it expands into a red giant. The Carina Nebula. Webb has also photographed a famous star-forming region known as the Carina Nebula, located some 7,500 light-years away. Hubble had captured images of a similar nebula known as the Pillars of Creation, which share a striking resemblance. Both images show streams of stellar dust and gas shuffling through space. And because Webb can see in infrared, scientists can see right through the Carina Nebula, revealing more young stars in the background, something no other telescope could accomplish before now. Looking into the past. Webb's dynamic instruments enable it to do more than just capture great images, but also to peer light years into the past. Webb can detect redshift wavelengths of light that trace back to as early as 108 million years after the Big Bang. This is mind-blowing to say the least, as we may soon have real-time images of the earlier stars formed after the Big Bang, which would give unprecedented information about the past, current, and future dynamics of our universe. What are you excited to see from the James Webb Telescope? Let us know in the comments below, and we'll see you in the next video.